Welcome, everyone. Thank you for your attendance here in the Zoom room and on the YouTube. It's a great pleasure to start the International Society of Electrochemistry Satellite Student Regional Symposium on Electrochemistry and the 50th Paulo Tengi Aula Sumojo School of Electrochemistry. My name is Thiago Paixão, and I am one of the organizers of this edition and the last one. Professor Roberto Torresi organized the previously 13 editions, and he was the person responsible for creating the school. Since 2014, the school received the name of Professor Paulo Tengi in his honor, and he passed away very close to the start of the 2014 school, and it helped a lot with the school project. This school is free of charge, and it was only possible due to the International Society of Electrochemistry and the Metron Auto Lab support. Additional, only 1 second to close the YouTube. And additionally, we would like to thank you other partners, the University of São Paulo Chemistry Institute, Office for Research of the University of São Paulo State Research Foundation, and the Research Center of Greenhouse Gas Innovation. Typically, ISE and Metron supported the accommodation for the students outside of São Paulo. Last but not at least, I would like to thank you all the speakers to join to this virtual project. Dr. Vitor Martins, Dr. Gabriel Meloni, Dr. Guy Denot, Professor Susana Torresi, and Professor Mauro Bertotti, as well Professor Roberto Torresi. The School of Electrochemistry is organized annually at the Institute of Chemistry of the University of São Paulo. The target of the audience is graduated students from young PhD from all over the world. Typically, participants are limited to 25 positions to ensure equipment access and develop the experiments in the small groups in hands-on physical conditions. The school has been working like that since 2005, putting together different students worldwide to learn and discuss electrochemistry. Last year, the school's physical edition was canceled due to the pandemic restrictions. The School of Electrochemistry is being organized as an online edition to return to the school's activities. Unfortunately, we will have no laboratory activities, which the participants recognize as essential in the previous events. But we will continually have distinct research worldwide to discuss theoretical topics on electrochemistry during 1 week, 3 hours per day. In the other model, we have normally 1 full day of discussions. This edition has a new record of registrations, and we received more than 290 registrations, and it was tough to select the candidates to be here in the Zoom meeting room. Thank you all that are here. We have now 40 participants. We received registration from 45 different countries. 50 participants were chosen to be here in the Zoom room meeting to interact with the speakers. With the support of ISE and the Metron Auto Lab, it was possible to stream the lectures on the YouTube too for the other 242 participants. Thank you all on the YouTube to be here now. I hope all of you enjoy the school and enjoy this electrochemistry week. Until to start, I will call to Dr. Carla Santana Santos. She will use the school space to announce a position on her electrochemistry group in German And Carla, the mic is yours.
Hello, everyone. Can you hear me?
Yes.
Let me share one slide. It's showing. So hello, everyone. Good afternoon, good morning. I'm Carla Santana, and I did my PhD in the University of São Paulo, and I had the pleasure to participate in the School of Electrochemistry in many years. And firstly, I want to recommend you to enjoy a lot this week, and I hope it is a good time. After finishing my PhD, I am now as a postdoc researcher in Bochum, in Germany, working with Professor Wolfgang Schumann. And then I asked like 5 minutes from Thiago and the organizers from the School of Electrochemistry to let you know that about a PhD position and also for postdoc position here in Bochum, as we have hard times regarding the conference for making this to share this information. Now I'm working with scanning probe microscopy on battery materials, and I'm starting a new project. And we needed like a new PhD candidates and also postdoc in this field. And I also wanted to, so if you have someone in mind, or if you are with some interest on this area, you can write me. My mail, it's right here. The lab has a lot of other opportunities. One can also visit the lab website. And I also wanted to shortly invite you also to another area that is more about biosensors with my colleague Felipe Consuelo, that is now a new PI in Lisbon, and he's really looking forward to new PhD students. So yeah, so please, just for you guys knows, and I highly recommend you to enjoy a lot this week. Thank you very much, Thiago. I think this was my message. Thank you.
Thank you, Carla, to announce. It's important to share this information with all here. Now, I will start the schedule. Until to start the schedule, I would like to talk a little bit how it will work, these Zoom rooms. And during the lectures, if anyone here inside of the Zoom room have some questions, raise your hand or write on chat, and I could open the mic to do the questions for the speakers. Or if anyone preferred to use the chat, I could transfer the question. I say the question for the speaker. And I think that's a good idea to how it works. There are two options: write on the chat or try to use the raise your hand, and I will open your mic to do the questions. Here we have a lot of 14 participants here now in the school, and once I will start our first lecture. And today, in this first day, we'll have the lecture from Dr. Vitor Martins from the University of São Paulo, Polytechnic School, talking about the electrode process. And here, Vitor is a chemistry graduated from Federal University of Londrina in 2008, and PhD in the chemistry from University of São Paulo in 2014. Research associated at the Chemistry and Biological Engineer Department of the University of Sheffield from 2015 to 2018, and at the Institute of Chemistry, University of São Paulo in 2014. And from 2018 to 2020, he was FAPESP Young investigator awarded at the School of Polytechnic School, the Polytechnic School, University of São Paulo, since from 2021 from today. Has experience in electrochemistry and on the development of electrochemical energy storage devices as battery and supercapacitors. Vitor will talk a little bit more about this on the last day, but today he will talk a little bit about the electrode process. Victor is with you now. Thank you to be here, and I will let you to discuss with all of the students and all of the researchers about your lecture today. Thank you again to join to this project, and thank you very much to help us with this.
Hello, good morning. Thank you, Thiago, for the introduction. Good morning, good afternoon to everyone around the world. Thank you for joining us today. I will share my screen now. Okay, you see my screen now, right?
Yes, Victor, is everything okay?
Okay. Thank you. So as Thiago said, the School of Electrochemistry is named after Paulo Teng. And Paulo Teng was one of the first mentors in the school. And he was responsible for this class, the first class in the week. So I'm really glad to be to have the opportunity to give this class in the school. I hope I can have the enthusiasm that he had when he gave this class for the other schools. So as Thiago said, I'm now in the Polytechnic School of the University of São Paulo. I'm working with energy materials, batteries, and supercapacitors, but we will talk about that on Friday, right? So today, the idea of this class today is to talk about electrode process and give an introduction for you so you can enjoy the next classes during the week, right? So first of all, I would like to make an introduction on the development of our understanding of electrical charge and how this field starts to grow, right? So humans have contact with electric charge for the first time, that was recorded for the first time, at least in books or writings, 2,700 years before Christ, right, before the Common Era. And that was when the contact of humans with the electric fish in the Nile River. This was the first contact that someone noticed that we have some charge and that you have some a different how can I say, a different way to touch them, but that fish behaved different than the other fish, right? So someone recorded that, and that was the first thing that was recorded related to electric charge. Then the first person to really start to make observations on the electric charge was Thales of Miletus in Greece, right? So this was 600 before Common Era. He started to make observations on the static electricity using amber. So he could rubber the amber in some feather and notice that it became static. It had some electricity. So Thales recorded those observations too. After that, we have, maybe you saw on the news in the last years, something about the Baghdad battery. This Baghdad battery was found in the Baghdad Museum a few years ago, I think like 5 years or a bit more, but it's recent, right? So this battery is supposed to be from the 1st to the 4th century. in common rigor already. And this battery is made of copper, iron, and it is said to have some acid solution inside it. It was empty when it was found, of course, but some analysis show that it could have some wine or vinegar inside this battery. The person that found this battery in the museum, or this object in the museum, said to be a battery, and the first battery that was used to store energy, and people use for some reason in that time. But this is highly disputed, right? So many people say that this object was used for another thing, and it's probably not a battery. So just to make a point here. And then the first discovery after probably Tales of Millets regarding the electric charge was the discovery of the attraction repulsion between the magnets, right? So he used the word for the first time as electricus, that in Greek means amber. So it's related what Thales reported like 1,000 years before William Gilbert. After that, we have the hypothesis of Benjamin Franklin and many others showed that lightning was related with electricity. And this was in the 17th century too. They could store this electricity in Leyden jar that was actually working like a capacitor in this time already. So that was the first time actually that someone could store energy, electrical charge to be used when needed. And then they could start doing some research, right? So you can store the energy and then use when you want to, or when we need to. And then we start to talk a little bit more on electrochemistry, actually. So Galvani discovered the bioelectricity, right? Touching the frog's leg with two scalps of different metals. He saw that the legs could move of the dead frog, right? So the legs could move when he was touching the legs with just metals. He thought that the energy was coming from the leg of the frog, and that the metals didn't have anything to do with the actual electricity. Only was making the movement of the energy in this case. But Volta disagreed with him and said that the electricity wasn't coming from the animal's leg, but from the metals, all right? And then with this idea, he invented the first actual battery. He made this voltaic pile, and this first battery helped to others to use it instead of the Leyden jar. The battery was a more reliable source for energy to do other kinds of experiments. So after that, the first light bulb was created. Humphrey Davy used carbon and the pile from Volta to create this arc lamp. So in 1821, Faraday invented the electric motor. And in sequence, Faraday also invented the electric dynamo that was important for energy generation. And by observations from Faraday, Auster, and Ampere, and formalized by Maxwell, had the unification of electromagnetism, all right, so 1861. After that, Thomas Edison showed the first stable incandescent light bulb. So this was 70 years after Dave's experiment. Then late 19th century, Tesla invented alternate current, the induction motor, and the polyphase distribution system. This revolutionized how we transport the electricity. And then just after all those developments, Thomson discovered the electron, right? So all those development were made before the discovery of the electric charge, the particle electron. And then a little bit later, Albert Einstein explained the photoelectric effect, right? So just to show you that a lot of electrochemistry was developed before the discovery of the electron. So after this timeline, I'd like to talk a little bit about the fields in electrochemistry and how it can be related to applications, right? So we have different fields like electrophoresis, corrosion. Then you have different kind of devices, so electrochromic displays or electroanalytical devices, batteries, fuel cells. We also have electroplating of metals in productions of aluminum and chlorine, for example. And all these fields have important impacts in the industry. So by electrophoresis, you can produce different chemicals. You can have extraction of metals, recycling, treatment, water treatment here, and then also destruction of toxic materials, surface finishing, and a lot of different industry are impacted by electrochemistry, right? And then you also have corrosion and all the impact it has on different parts of the industries. Have batteries and fuel cells, sensors, analysis, and also medical monitoring and procedures. So just to have a look on how electrochemistry can be applied in different places, right? With that, I would like to show you, before we actually talk on the reactions, but just to show you a few of these common electrochemical reactions, right? So just to say that in electrochemical system, we are concerned with the process and the factors that affect the transport of charge across an interface between chemical phases, right? So we have different chemical phase, and there is a charge crossing this interface. And those reactions, I have some examples here. So we have cathodic reactions, so we have reduction of something, and we have anodic reaction. You have the oxidation of something, right? So here I have a list of common reactions that you see in lab or also in the industry. So let's think a little bit, what is electrochemistry, and what is the difference of common redox reaction and actually electrochemistry. So in electrochemistry, electrochemistry is the branch of chemistry that is concerned with the interrelation of electrical and chemical effects. As I said in the previous slide, in electrochemistry, we are concerned about the charge that's crossing that interface, right? So here we have an example of a redox reaction. So we have a zinc plate here inside a copper sulfate solution. And then we have the oxidation of zinc. So zinc is coming from zinc 0 to zinc 2 plus, and we have copper 2 plus that is being deposited on the plate, on zinc plate, as copper 0, right? So you have electron transfer here, and you have two redox reaction, right? Why can we say that this is not actually electrochemistry, although they are two redox reaction, and we have our overall reaction here with electron transfer. Because in this case here, we don't have actually the use or measuring, or we are not applying the voltage for this to happen, right? So here we have redox reaction, but we are not actually concerned on the potential for this to happen, right? In actual electrochemistry, we have external circuit going through a voltmeter or ammeter or apply a current or voltage, or measure a current or voltage. So here we have exactly the same kind of reaction occurring. So both semi-reaction, half reaction are occurring in here. So we have the zinc plate, and in this case we have a copper plate, and you have the zinc oxidation on this beaker here, and then we have the copper reduction plating on this copper plate here. So if you see, you have exactly the same overall reaction than we have in this case here. But we have external circuits to measure the voltage that this is occurring. So we have a flow of electron from one plate to the other. So here we are doing actually electrochemistry. So electrochemistry can be used as a tool. So you can generate intermediate or measure some properties of the system, for example, concentration. Or it can be used to power some device. So we are using the flow of electron for something else, right? So as a battery, when we have the reactions in a battery, you have the flow through the external circuits, electron flow through the external circuits, and you are using this flow to do something else. All right. So in here, just to for you to remember that we have the same reactions. All right, so let's think now about the electrochemical cell, mainly in the cells that we use in the lab. So this is a typical cell used in our research lab, but you can also have different type of cells, right? In this cell here, you have like a beaker, a glass, with a cap. This cap has some holes, and you can place electrodes in these holes. So you have, in this case, 3 different electrodes. We have a counter electrode, a reference electrode, and a working electrode. You will see through this week the hole of each of these electrodes. You also have the electrolyte solution. And in this case, you can see that we have holes for gassing or degassing, or adding some reagents to the electrolyte during the experiment. Just to remember you that I said in the previous slide that we are concerned about the facts, the process and factors of the transport charge across the interface of chemical phases. So if you see here, in this case, you have a solid electrode and a liquid electrolyte, and then we have an interface between just two phases. And these two chemical phases, the electrochemistry will happen in between just 2 chemical phases. You have an electronic conductor, in this case is the metal in the working electrode, and ionic conductor, that is the electrolyte. So typical electrode materials, the electrode materials will be responsible for carrying electrons are holes, right? So we have solid metals like platinum, gold, copper, and aluminum. We can also have liquid metals, as mercuries and some amalgamas. Can also have electrodes based on carbon, like graphite, activated carbon, glassy carbon, boron doped diamond. And other types of electrode materials are semiconductors, as indium thin oxide, silicon, and other types, right? And in the electrolyte, we can vary a lot the composition. So the electrolyte will be responsible for ions to move, so the charge is being carried by these ions. And we have different types of electrolytes. So you can have liquid solutions, so normally containing proton, sodium chloride. And this liquid solution can be aqueous or non-aqueous solvents. So you can have organic solvents or like ionic liquids, different types of liquid solutions in here. Can also have molten salts, polymers, so ion conductive polymers, and also inorganic electrolytes, solid electrolytes. So we have the cell, like I said before, with different types of electrodes, right? So we have the working, the counter, and the reference electrode. And then you connected it to the potential stat that you have in the lab. Most of the potential stat today, you see that we have 4 types of wires. So you connect 4 wires to the 3 electrode cells. And you see that each of these wires is responsible for carry something, right? And you will be the contact between the cell and the potential stat. So you use the potential stat, you can use in 2 different ways. So you can use as a potential stat or a galvanostat. So you measure or apply a potential or a current, right? So in potential stat mode, you control the potential and measure currents. And in the galvanostat mode, you control the current and measure the potential. Things that we will measure, like cell potential, you'll be measuring voltage. And voltage is the energy by the electric charge. So voltage is joules per coulomb. Remember that. So it's the energy to drive a charge that go externally between these 2 electrodes. So this is the what will drive some reaction to occur. And the cell potential will determine if a reaction will occur, the rate of the reaction, and also the direction. This will be clear in the next few slides, right? So when we will talk a little bit about the impact of the cell potential, but just for you to know that in the potential stat or galvanostat, you see the cell potential. Actually, you can also see the electrode potential depending on if you have 2 or 3 electrodes. But the cell potential or electrode potential is actually the energy to drive the charge externally between 2 electrodes. Remember that. So in a 3 electrode cells, you have, as I said, the working electrode. That's where the reaction of interest will occur. So if you have a 3 electrode cells, the working electrode is responsible for what we are seeing in the potential stat or in your computer screen, right? So the counter electrodes, you allow the electrons to flow through to or from the working electrodes, just for you to have a circuit for the electrons to flow. And the reference electrode will be used so the working electrode can have its potential measured against something. So the reference electrode has a constant potential that we know, and then you measure this potential against the reference electrode. The reference electrode has a constant composition and a stable potential, right? So by convention, we have that the platinum hydrogen electrode, when we have activity of protons as 1, we have that this potential is 0 volts. So this is called the normal hydrogen electrode. So remember, this is by convention, right? So everything that you see, UV versus something, some reference. So other reference electrodes that are more used than the hydrogen electrode are, for instance, the columnar electrode, that's mercury chloride, unsaturated chloride, and it has a potential of 0.242 volts versus the normal hydrogen electrode. And you can also have the silver chlorides, unsaturated chloride, and the potential will be this 1 volts versus the normal hydrogen electrode. So remember that the convention, the potential equal to 0 volts will be the platinum hydrogen proton with activity as 1. So here we have like a demonstration of how this works, because we have platinum that is solid electrode, like a metal electrode, right? And then we have a gas, and then we have protons in solution. So how do you do this experimentally? So we have a platinum wire here, you have a solution with protons, and then we can bubble the gas near the platinum electrode. So this will be the normal hydrogen electrode. And the other example here is a silver wire, and then we have silver chloride that's insoluble in water, right? So you'll be just solid in contact with silver, and you also have chloride in solution. So these are the 2 examples of reference electrodes here. So it's important to remember that we are observing or controlling the electrons of the working electrode. In a 3-electrode cell, so if you assemble the cell, connected the potential stat to the cell, what we are seeing in the screen is related to the working electrode. So if you are just measuring the potential, you are measuring the potential of the working electrode against the reference electrode. If we start to applying anything, current or potential, this the observations are related to the working electrode. So it's important in here to remember that the reaction that we are interested happen at the working electrode surface, but the counter electrode will also have a reaction, because the electrons need to flow to or from somewhere, right? And an electrochemical reaction will occur at the counter electrode to balance the reaction that's occurring in the working electrode. So the counter electrode needs to be big enough so it can offer or accept all the electrons that the working electrode needs to give or receive. All right, so the reaction that's occurring in the counter electrode needs to be something that will not contaminate the electrolytes or create any disturbance near the working electrode. So the message that I want to tell in here is we are concerned, we want to understand the reaction occurring at the working electrode but we need to design well the electrochemical cell. So the reaction that's occurring at the counter electrode does affect what we are measuring, right? And also the reference electrode needs to be has a stable potential. So all your measuring, you will be referenced to this reference electrode. Okay, so I told you before about the 4 wires, and that they each of these wires will carry something, right? So here you have again the cell connected to the potentiostat, and we have a potentiostat with 4 wires. Normally we have 2 wires connected to the working electrode, and then we have 1 wire connected to the reference electrode, and then another wire connected to the counter electrode. Why do you have all these wires, like 4 wires, if you have 3 electrodes? So because each of these wires will carry a different thing. So in this black wire here connected to the counter electrode, you carry currents, right? You carry the currents between the counter electrode through the external circuit and then to the working electrode. So if a reaction is occurring here in the working electrodes, let's say oxidation is occurring here. So we have a flow of electrons going through here, going to the current wire, to the external circuits, to the counter electrode, to a reduction to occur here. Okay, so those 2 wires are only concerned about current, but we are also measuring a potential. So this potential will be measured against between the working electrode that has the potential wire connected to it, going through the external circuit, back to the reference electrode. All right, so the potential that the reaction is occurring here. So if we're applying a current for a reaction to occur, the potential will move for that reaction to happen. And then to measure it, we have these 2 wires here. So we're measuring potential of the this electrode here against this one. So what if you have only 2 electrodes? You don't have 3 electrodes. So we don't have a reference electrode. What we will do is connect the second potential wire to the counter electrode, right? So then we have currents going through the external circuit to the current electrode, and the potential will be against the counter electrode too. What's the problem here is that we are having reactions occurring here, and you don't know exactly what potential this is happening. So the difference of potential that we are measuring between the working electrode and the counter electrode in a 2 electrode cell will be more difficult to determine. We will have a number, but will be a number versus the counter electrode, right? So to do that, we need to ensure that we don't have any change of potential during the electrochemistry occurring there. So basically, what I'm saying here is that what will happen with the working electrode when we apply a potential, right?
I'm not sure I understand.
So what we are doing is changing the energy level of the electrons in the working electrode. So you have the energy levels of the electrode at equilibrium. So when we apply a voltage using your potentiostat, so we're applying a voltage against the reference electrode, you are changing the energy level of the electrons inside the electrode, right? And you will see how this will affect the interface between the electrode and the solution. So let's think about a reduction process here. So you have a species A being reduced plus 1 electron here, and then you have an ion here, right? First, what you do is apply a potential, so you change the energy level of the electrons. So we're applying a negative potential, right? And then the energy levels will go up. With that, we have that the energy levels of the electrons in the electrode will be higher than the energy level of the LUMO orbital of some species in solution. So if you have this case, if you have enough potential, negative potential to go through the LUMO here, you have the electron transfer from this energy level to the species in solution. So here we have a reduction, right? And we can also have the other way around. So we have species A losing an electron, turning an ion, and it's exactly the same thing. So then we go down with the energy level of the electrons, applying a positive potential. So applying this positive potential, the energy levels of the electrons in the electrode will go down. If you go down enough beyond this, the highest occupied molecular orbital of any species in solution, then you have electron transfer from species in solution to the electrode. So what we are actually doing when we are doing electrochemistry is playing with the energy level of the electrons in the electrode. So if you do enough, high enough or low enough, so we are not in between the highest occupied or the lowest unoccupied. If you go beyond this this energy level for any species in solution, it doesn't matter if it's a solvent or if it's a solute inside the solution, the reaction will occur, right? So do you have any questions?
No questions yet in the chat.
Okay.
But for everyone in the room, if you have questions, again, put the questions on chat or try to raise your hand.
Yes, please. So the critical potential, let's say, if you go to the energy level that is exactly the same as the highest occupied molecular orbital, for instance. So the energy level of the electrons in the electrode is the same as the highest occupied molecular orbit, or the same as in the lowest unoccupied. This means that you have the standard potentials. So that is the standard potential for that reaction to occur, or for the reduction, or for the oxidation. All right. So this will be specific for each reaction. So depends on what you have in solution. So let's think a little bit about what we measure and the amount of things that happen in the electrode, right? So you see that we have transfer of electrons occurring depending on the energy level of the electrons in the electrode, right? And the amounts of electron that is being transferred from the electrode to the species in solution, or the other way around, from the species in solution to the electrode, the amounts of electrons will be the charge of this process. So charge will be in Coulomb, right? And 1 Coulomb is this amount of electron here. So when we have this amount of electron being transferred during this electro process, means that we have 1 Coulomb. All right. And then we have the Faraday law of electrolytes that related the amount of species being reduced or oxidized. So you have a relationship between the amount of species being reacted that will be equal to the charge of the that is consumed or gained during this process, divided by a constant, that's the Faraday constant, and the number of electrons in this reaction, all right? So then you have the number of moles of species being produced or consumed. So this is the Faraday constant. You have here the number in coulombs. So if you have Z as 1, that's 1 electron being transferred per reaction, you have that this amount of charge, 96,000 coulombs, will produce 1 mole of product, right? So if you have here exactly the same thing as the Faraday constant, and you have 1 electron per reaction, then you have 1 mole of product, all right? And just to remember you that with that, the current is the flow of electrons, right? It's the measurement of the flow of electrons. So we have that 1 amp is equal to 1 coulomb per second, all right? So 1 coulomb per second is how much charge is going through this interface per second. That's flux of electrons or flow of electrons that's measured in amps. So 1 amp is 1 coulomb per second. This is an important thing to remember. Another thing with that is that the current that we are measuring or apply is proportional to the chemical reaction that's taking place in the electrode or in the interface. So let's think a little bit about potential that we are measuring when we assemble a cell, right? So we have here a 2-electrode cell. So we have a platinum electrode, so just metal here connected to the external circuit, and we have a silver bromide electrode, also connected to the external circuit, and we have a solution with HBr here, 1 molar of HBr. So just to show you that we have some type of notation, I see we have something in the chat now. So this is a type of notation for this cell here. So what does it mean? So platinum electrodes slash proton bromide. So the slash means that we have different of phases. So we have platinum, in this case, in the solid phase, slash something in another phase, that is proton and bromides in aqueous. So the comma here means that these 2 species are in the same phase. So we have the concentration of these species, and then we have another slash, silver bromide, another slash, because we have different phases here. So this is 1 solid, and this will be another solid. So silver bromide and silver. So this is the notation that we have. So if I give it this to you, you can understand that we have exactly this cell here. One question that you can have is, what is the cell potential while we connected this cell? So what is the open circuit potential? Thiago, should I stop and see the questions here?
It's not a question. It's only a salutation for everyone.
Okay, because it's popping up here in my screen.
Oh, you could close. I will check for you the questions.
Okay, thank you. So if you think, remember that I said that measurements are made against something. So I talked about the 3 electrode cell and the 2 electrode cell. In this case, you have 2 electrode cell. So the measurement is of the platinum electrode against the silver bromide electrode. And what is the potential that the potential stat will read when we don't have any flow of electrons? So there is no reaction occurring. We are not applying any current or any potential. What is the open circuit potential? So we know that silver bromide electrode in contact with this HBr solution will be in equilibrium. So we have this equilibrium here. We will talk a little bit later on equilibrium, but just for you to know that electrodes that are in equilibrium, you have the reaction occurring. Both reactions are occurring at the same rate. So we have the reduction reaction here and also the oxidation reaction happening at the same rate. And when we have this equilibrium, you can calculate the potential of that electrode using Nernst equation that we will see later today and also again tomorrow. So you have a table with many reactions at equilibrium, and then we know that the potential of this electrode is 0.0713 against the normal hydrogen electrode. All right. So you know the potential of this electrode here, but what is the potential in the platinum electrode? There is no equilibrium reaction on platinum electrode, so we can't use Nernst equation to calculate the potential between these 2 electrodes. So we don't know. We only know a potential of 1 electrode, and we don't know of the other electrode. So let's consider the changing potential to see if you have some clue on the OCP. So let's assume there is one OCP that we don't know yet, but we start to scanning from this OCP towards negative potential. So it's moving from somewhere here to the left on this graph, so going to negative potentials, right? And then at some point, we'll have some currents increasing here. This is the onset of reduction of protons to hydrogen on the platinum surface, all right? So we have protons in solution, it's gaining electrons and producing hydrogen. So you start to see some bubbles in the platinum electrode. And then we keep increasing the potential and the currents keep increasing. Going towards negative potential, right? So we are increasing the negative of the potential in there, and then we are increasing the currents that we are measuring. So remember that we are controlling potential and measure current in this case. So as I said before, if you have one reaction occurring at one electrode, you need to have some reaction occurring in the other electrode. So we have reduction of hydrogen here, and you have to have an oxidation of something in the other electrode. So we know that this electrode is in equilibrium here, but now we are forcing it to go to one direction. So one reaction will occur faster than the other, and this will be the oxidation. So we have silver bromide going to silver here, metallic silver, right? So silver 0, and going to silver bromide here in this reaction occurring in the second electrode. So we assume that there is no change in bromide concentration here, and just assume that we have enough concentration for this reaction to occur. So this is happening when you go towards the negative potential. So let's think about the scanning towards positive potential. Then starting from somewhere here again that we don't know yet, you start to increase the potential positively here, and then we have an onset on the bromide oxidation on platinum. So you see the oxidation of bromide forming bromine, and it's losing electrons here. All right. So this is happening on the platinum electrode, right? So we are this is the working electrode in this case. So bromide is being oxidized on platinum electrode, and so the electron needs to flow to the other electrode now. So we are being oxidized, so electrons are flowing to the other electrode, and then another reaction will occur in the silver-silver bromide electrode. That will be exactly the opposite reaction that we had before. So assuming again that there is no change in bromide concentration in solution. Okay, so now we have this curve here. You see no current increase in this potential window, and current increasing on those potentials, depending on what kind of reaction is occurring. But the truth is that we don't have the cell, the open circuit potential of the cell yet. So again, we have of one electrode that goes from the inertial location. You have potentials of reactions that occurs when we apply different potentials, but we don't know the cell potential while the circuit is open. So what is the cell potential here of the OCP potential when nothing is happening? There is no open circuit potential to be known or calculated here. There is no equilibrium reaction in platinum. So the measurement that you do during this case will be anything between this value to this value. So the OCP will be around those values here, and you probably be doing some impurities in the cell, like oxygen or anything else, right? So it could assume any value here because the platinum electrode has no equilibrium reaction on its surface. So it could measure anything. Could it measure something around here? No, because for the potential to be in this region, we need electrons to flow, and we are not applying anything. So we're just measuring the potential while the cell is open. Could it be here? No, because there's reaction occurring here too. So it will be any value on this range here. And will be probably due to some impurities like oxygen or some impurities in the salts that you use it, something like that. Okay, so we talked how using electrochemistry, we are playing with the energy level of the electrons, right? So if you have, in this case, on the left, we have a platinum electrode in contact with a solution. This solution has protons, chromium, zinc in solution, and we start to play or to change the energy level of the electrons of platinum electrode here. Let's see what will happen, right? So if you increase the potential going through zero, so potential here is volts versus the normal hydrogen electrode. So the OCP here of the cell, when we are not applying anything, it will be anything below 0 volts, right? It's going positive here in this direction. So be any value around here before 0 volts. So there is no reaction occurring. So potential for current equals to 0. So we're just measuring. Then we start to applying a negative potential. So we are increasing the energy level of the electrodes. Remember that applying a negative potential is to increase the energy level of the electrons in the electrode. So we go through zero, so we pass zero, and then this reaction will occur at the electrode surface. So you have reduction of protons to hydrogen at the platinum electrode surface. If you keep increasing, then both and go through this value here, then we have that both reactions will occur, right? So you have enough energy of the electrons for hydrogen to be reduced, and also we have enough energy now for chromium to be reduced. So both reactions are occurring at the same time. So the current that we are measuring in a potential like that will be due to two electrochemical reactions occurring at the same electrode. So for this case is for platinum. Let's change for mercury here. So the potential that we measure for current is equal to 0 is here. All right, so there is nothing happening in the mercury electrode. And then we start to increase the energy level of the electrons in the mercury electrode, and they go through 0, but we don't observe any reaction occurring. So let's say that we are doing this experiment and we are observing this. So we go, the energy level goes through 0 volts here, and this reaction is not observed. Nothing's happening yet in the electrode. And then we keep increasing the potential, and then chromium starts to reduce. You see that chromium is reducing, but hydrogen is not being produced in the mercury electrode. So why it's happening? Why don't we have the reduction of hydrogen in the mercury electrode if we have enough electrode potential for this to happen? Sorry. So we have enough energy to drive the reaction, but the reaction is not occurring as it happened with the platinum electrode. There's one thing to say. So the electrochemical reaction, it can be thermodynamically favorable. So the reaction should happen, but it have a slow kinetics. So the reaction happens so slow that we are not observing it. So the current will be really, really small. All right. So it's favorable to occur, but it occurs so slow that we can't see it. So you can't even measure it, because the current, you see later today and tomorrow, that the current is the measurement of the rate of the reaction. So if we have a slow kinetics for this reaction, we have a very small current to measure. So this is why the hydrogen reaction is not occurring in mercury and in platinum. But you can ask me, but this is the same reaction. So why one have a slow kinetics in mercury and fast kinetics in platinum? Because you have a different interface over there. You have like platinum metal is a different contact with the solution than the mercury electrode. You have some catalytic effects in the platinum that we don't have in mercury. So the catalytic effect will help what? Will help the kinetics of this reaction to occur. So you have the same reaction, but using different electrodes, and the reaction is fast in one type of electrode and is slow in another type of electrode. So we have a catalytic reaction occurring when you use platinum. So that's why people use platinum to produce hydrogen, right? So it's really catalytic reaction over there. So
Vitor,
yeah,
we have a question in the two questions now in the chat.
In chat?
Yeah, there is one first. Understood the range in which OCP should be, but how to determine the OCP and the factors changing the same? Could you elaborate a little bit more?
Yeah, so I'll go back one slide. So in this example, we have two electrodes, right? So one electrode has a reversible equilibrium reaction occurring here. So these two reactions, here you understand that we have two reactions, right? So one goes to the right and one goes to the left. The potential that these reactions occurs at the same rate, so the both reactions is occurring at the same rate, is known, right? So this is the potential. And platinum in this solution, it doesn't have any reaction to occur in equilibrium. So there is no oxidation of platinum, reduction of platinum at the same rate occurring in this system, right? So what's the potential of this electrode? We don't know. It's not possible to measure this potential. The only thing that we will measure will be the difference of potential between these two electrodes. And as we don't have an equilibrium reaction occurring in this electrode, it could be anything, any value between the potentials that there is no reaction occurring at that potential, right? So if you go to 0 volts here, what do you have? We have hydrogen reduction. So it can be 0 because for the potential in the platinum electrode to be 0, you need to have a flow of electron. Could be 1 or 1.2. No, it can't, because for the potential of the platinum electrode to be 1.2, it needs to have a flow of electron. So there is a reaction occurring here. So it will be anything between here and here, and we can't say any value, right? But the potential is that we measure something, and this value will be related with something that is in solution, and could be any impurity. But the value is unknown. We can't know the value of the OCP. We can't calculate it. We can measure it, but we can calculate it. I hope that answered the first one.
Yes, there is another one from Andrea. So if I decrease the potential more, I would see the reaction of proton reduction also in mercury electrodes.
So when we are applying, let's say, more potential, you are increasing the energy of the electrons, right? So at some point, you will see the reaction to occur, but we have a much higher potential. So yeah, if you see the first slide that I show, sorry. So current keep increasing when we are applying more potential, right? So at some point it will occur, but you see that for platinum electrode, the voltage, the potential is much smaller. So yes, at some point it will be high enough energy level for the other reaction to occur too. All right.
Thank you, Vitor. No more questions in the chat.
I'm fighting with the software now. Okay. So yeah, just to finish this part, thermodynamics tell if a reaction is to happen, and kinetics tell how fast or slow it will happen. All right, so remember that. So, so we have two types of processes occurring in the electrode. We have Faradaic reactions and non-Faradaic reactions or process, as we will. And these two types of process occurs at the electrode, right? So we'll see now separately those two types of process. But just for you to know the difference between them now is that Faradaic reactions, we have charge or electron being transferred across the metal solution interface. So there is electron being transferred across the interface. The reaction will follow the Faraday's law of electrolysis, and it's called a Faraday reaction, all right, because of that. So remember that the Faraday's law of electrolysis, you can calculate the amount of product that is being produced or anything that's being consumed by this reaction. This is very important because we can measure or calculate concentrations or things that are being produced with the current that we are applying or measuring. A non-Faraday reaction, there is no charge transfer between the interfaces, all right?
Sorry, Vitor.
Oh, yeah.
We have only one comment here in the chat. Do you recommend platinum wire as a counter electrode for OER?
ER?
I think that is OCP or.
So that depends a lot on your cell, actually, you know, because remember that I said that what we are measuring is what is happening in the working electrode. So the counter electrode needs to be something that will give or receive the reaction, the electrons of the working electrode reactions. So let's say if you have a very small working electrode in a very large counter electrode, and you have a Faraday reaction, so you have transfer of electrons going through the interface of the working electrode, but it's so small that only the non-Faraday process that's occurring in the counter electrode will give or receive enough electrons to balance this circuit, you know. So really depends. So if you have a big working electrode, you need to work with a big working electrode. You need to have an even bigger counter electrode for this case, right? But let's say that we have electrode of same size. You can't work with a very large counter electrode. Then you need to think on the reaction that's occurring on the counter electrode, because you produce or consume something, and changing the electrolyte in the cell can affect the measurement that we are doing in the working electrode. So there is no perfect counter electrode. Let's say use this one because this one's the best one. That you really need to think on the design of your cell. All right. So for example, in energy storage research, we have normally we use standard counter electrodes. For example, if you are using studying lithium-ion batteries, you use lithium as a counter electrode. And for example, if you are using if you are studying supercapacitors, you can use activates carbon. And then you need to play with the size of these counter electrodes in the cell. But I will talk about that on Friday, all right? So for your question now, I can say that there's no perfect counter electrode for all the cells, in the lab. You need to think on the reactions that are occurring and the design of the cell, okay?
I think the question matches. OER is the oxygen evolution reaction, but it's the same. Your answer
yeah, so
is perfect. Yeah. There is another one. Sorry, Vitor.
Okay.
From Luan. And what's the difference between NHE, the normal hydrogen electrode, and RHE?
Yeah, so it's same notation. So it's the same electrode. You don't need to worry about that.
Yeah, because he mentioned that he always see in some manuscripts, and how can I convert the potential, but they are the same.
Yeah, so NHE is normal hydrogen electrodes, and RHE, I think it's reference hydrogen electrode, right? It stands for, yeah. So you can see both of them. So they are interchangeable. Okay, so back
No
to
more questions here.
no more.
Sorry, Vitor.
No, no worries. Can stop me anytime. So back to non-Faraday process. So you don't have any charge transfer reaction occurring. So there's no transfer of electrons in the interface of metal solution. But the process, the non-Faraday process, will change the metal solution interface. All right. So the difference is in there. You have some changes in the interface, but there's no electron crossing this interface. So, sorry, this is known as non-Faraday process. This is important here. So there is no charge transfer, but electrons will flow in the external circuit during a non-Faraday process. All right. So I hope I can convince you in the next slide of this affirmation here. So this is very important. There is no charge transfer, but there is electron flow in the external circuit. Okay, so the non-Faraday process is related with the electric double layer. Probably many of you already heard about it. So let's think about a metal electrode in contact with a solution. So let's say this is the OCP. So this is the open circuit potential. And then you have an equilibrium here. You don't have any potential driving anything. So if you go to positive potential, but this positive potential is not enough to drive a reaction, right? So there is no electron being transferred. You are just polarizing the electrode positively. Then just positive charge will attract anions, right? So ions of negative charge, you counterbalance the positive charge in the electrode. And we have the opposite thing on the other direction. If you have a polarization of negative potentials, you change the interface here. So the electrode is now with excess of electrons, and then you attract the cations. So cations, you balance the charge in here in this interface. So I said in the previous slide that phrase that is changing the interface, but there is no current, there is no electron transfer between the interface, right? There is no electron being transferred from the anion to the electrodes here, but you changed the interface. It's not more like it was when the electrode was at equilibrium. Okay, so if you think a little bit on this cartoon here, you have two layers of charge. That's why it's called double layer. So we have a positive, in this case, a positive layer in the electrode and a negative layer in the solution. So this resembles a capacitor. So capacitor, like in a physics capacitor, you know, so you have two layers and one interface between them. And the nice thing of it is that we can store energy in these capacitors, right? So in this double layer, and they resemble the physical capacitors. So you have that capacitance will be related with how much charge is stored depending on the potential, all right? I will talk a little bit more on this electrical double layer and present to you the different models and the understanding that we have today. So let's assume that this gray area is the electrode and this blue area is the solution. So you have the electrode in solution, nothing is happening. We are not applying anything here. And then we start to apply a potential. What will happen is that we will change the electrode surface here in contact with the solution. So you have the space charge region here. So we have, let's say that we are applying a negative potential. So applying negative potential is placing more electrons in the electrode surface here. This will impact the region inside the solution too that is in contact with the electrode, all right? So in this region here, we have the double layer. So the change in the metal is really small. So it's really, really small, this change in electrodes in the metal, but it changed, all right? So the potential here is changed. And then the thickness here of this change in the electrolyte will depend on concentration, right? So we'll see with the models how this changed. But the important thing is that we have this interfacial region here of the contact of bulk electrode and bulk solution, and the region that is changed, all right? There's no charge transfer, as I said before, but the regions are charged. So we have charge in the electrode surface, and we will have charge on the electrolyte region close to the surface of the electrode. And the important thing here is that the charge of the metal is equal to the charge of the solution. So the charge is balanced here. So the net charge is 0, but you have charging potential in metal and charging electrolytes. And the charge on the metal, you vary with the potential. So if you increase the potential, the charge on the metal will increase. And then if you decrease the potential, making it more negative, you have the charge will be more negative. And remember that the charging solution, you balance the charge in the metal, all right? So charge is increasing in both directions. It's just changing if it's positive or negative charge. And then we have a point where the metal charge is 0. And then we have this potential, right? So this potential here, we talk a little bit later about it, is the 0.0 charge, potential of 0 charge, right? So this is the charge, this is the potential where there is no charge stored in the electrode and in the electrolyte. So if you differentiate the charge here, you have the capacity. So you see that you have the potential of 0 charge here, and then the values of capacity of these regions depending with the potential, right? So this is just differentiating this curve here. So this is a thinking process, right? And this is what people measured back in the days. Here we have different electrolytes and measurement of the capacity of the double layer for different potentials. You see that they have a profile similar to what we are thinking here before, and it does change with concentration of electrolytes. This will be important for the development of the different models. We will see this graph later again. Just for you to know that the first models was made thinking on experiments made with mercury electrodes. All right, just some information. Okay, so the first model was the Helmholtz model, was described by Helmut in 1879. Just for you to remember that this was before the discovery of the electron. All right, so the first electron double layer model was made before the discovery of the electron. And what Helmut proposed? He proposed that we have points of charge in the electrode. So the left here is electrode and right is solution. So you have points of charge in the electrode, and you have points of charge in the solution to balance this electrode. And the important thing here is that this layer is rigid. So there is no movement of ions here. So it's balancing the charging and it's a rigid layer. It has a thickness. So the thickness is going through the middle or the center of the ions here. So this is the thickness of this layer in solution. All right. So remember that the layer in solution is much bigger than the layer in the electrode, and this is basically the layer of the thickness of the double layer. In this first graph here, you have the how the potential is changing with the distance to the electrode. So in here we have distance 0. So you basically have potential of the metal. And then when you walk far from the electrode, the potentials drop until you have the potential of the solution. All right, and this is the thickness of the double layer proposed by Helmut. So you drop from the metal potential to the solution potential in a straight line. Important considerations here that charges are ordered in a rigid way, and it resembles the capacitor as we said before, right? And as you resemble a capacitor, you can calculate the capacitance or the capacity here of the double layer, considering the dielectric constants of the medium, permittivity of vacuum, and the thickness of the layer. So calculating that, we see that this model results in a capacitance that is constant. It doesn't is constant over the potential, right? So here you have capacitance and potential, and you have the same capacitance or capacity for all the potentials. And you see that is not exactly the case as I showed before. So the major drawbacks here, it's not considering interactions with the layers, all right? And it also does not consider electrolyte concentrations. And then you saw in the previous slide that we have changes in the capacity of the double layer with concentration. Okay, so later, 20 years later, independently, Gui and Chapman developed another model for the electrode double layer. So the first thing that they thought was that the electrode wasn't behaving as a specific point charge in every space like before. So the electrode actually behaves as a giant ion. So as a giant ion, the electrode will interact with the solution with the small ions, right? So with that, they consider that the relation in the interactions of the ions in solution and the giant ion that is the electrode would obey Poisson-Boltzmann and Debye-Huckel equations. So the first thing in here is that concentration matters now. So if you see this graph here, the calculation of the potential drop for this model in function of the distance to the electrode is that we have different drops for different concentration. So in this case, is for a smaller, lower concentration, here for a higher concentration. So we have a different drop of the metal, of the potential from the metal to the solution. So in here, they added the random thermal motion. So that's the Boltzmann law, right? And then with that, they could see that the movement of the ions matter. It's not just a rigid layer of ions, but the ions that's participating in the double layer or participating on balancing this charge won't be rigid. They will move depending on the Boltzmann law, right? So this layer was named as diffuse double layer because it has these ions movements. The nice thing here is that using Poisson-Boltzmann and the Hooker equation, they could calculate the capacity of this double layer, and you see a curve like that for capacity over potential. First thing that is interesting that we have a dependence of capacity with potential, right? That we didn't have before with Helmholtz. And we also have this potential of zero charge here. So it's potential where the capacity is minimum. How this capacity of this potential of zero charge is acquired is because you have this, in the capacity equation, we have this Cauchy term here. And then if you don't have a difference of potential, that is this term here. So this is the difference of potential. This will be zero. This term will be zero, and Cauchy of zero is 1. And then we have just this value here, and then the capacity of the double layer at zero, potential of zero charge, or no over potential, right? It depends on these values here. So thermal motion, concentration of electrolytes, and charge of the electrolyte. So easy means no difference of potential, remember? The other thing is that when we change potential, so we are changing this term here, we are resulting in a capacity that will have a Cauchy profile. So potential is changing here, so this number will depend on this term. As potential grows, this grows in magnitude. So this is a Cauchy form, right? So at some point here, the capacity will be so high that the potential doesn't matter anymore. So this is one of the drawback of this model. So experimentally, the measured thickness of the double layer in this model is greater than the calculator, right? So this is another drawback here. Let's compare Chapman Helmholtz model. So with what was measured, all right, with the sodium fluoride in mercury electrode. So you see Helmholtz has acquired a constant capacity over potential. That's not exactly the case for the whole measurement here. And Chapman had a good describe of capacity of the double layer near the potential of zero charge, right? So this part here we're seeing as well, this part. But if you look well here, when we start to increase even more the over potential, it starts to resemble a little bit Helmholtz at larger over potential, right? So let's see what people did before that. So the next model was by Stern in 1924. And what he did was exactly considering the sum of these two models to resemble the experimental data, right? So Stern model consider both layers, the Helmholtz layer and the diffuse layer. So it considers a compact layer here. So we have a ions in contact with electrode that will be rigid. So this is the compact layer, so they're not moving. And you have the diffuse layer here. That is the ions that will be there compensating charge, but we will have the thermal motion as proposed by Gui and Chapman. And the profile of the decay of the drop of the potential in function of distance of the electrode, you have two regions too, right? So you have a linear decrease here that is exactly as the helmets layer, and then you have this decay as proposed by Gui Chapman. So we have here the distance of this rigid layer. So what this tells us is that the capacity or the capacitance of this double layer resembles the sum of two capacitors, because you have the capacitance of the compact layer and the capacitance of the diffuse layer. So we know that two capacitors in series, you have, we obey equation like that. So it's the sum of the inverse of the reciprocal of these capacitors, of this capacitance of each layer, right? And in an equation like that, you know that the total capacitance here, or the double layer capacitance, will be determined by the smallest one. So the smallest value here will gain the total value, right? So we see that the profile of the capacitance over potential will depend on which capacitor is smaller in this model, right? So it combines both profiles of Helmholtz and Gui Chapman. So near the potential of zero charge, the capacitance of the double layer will be much larger than the diffuse layer, and so the total capacitance will be equal to the, sorry, it's the other way around here. So close to the potential of zero charge, the capacitance of the double layer will resemble the capacitance of the diffuse layer, right? And then you have this profile here. And then far from the potential of zero charge, you have so much potential over there that you are making this rigid layer stronger. And then the capacitance will resemble of the double layer. And then we have the sum of these two profiles that we saw before. So if you compare here, you have that the red one is the Gui Chapman, that you have nice profile for potentials near the potential of zero charge. And then we have helmets that have nice profile far from the potential of zero charge. And then we have a Stern model that combine both, and then resembles better the experimental data. Okay, so this Stern model already resembles well the experimental data, but more models were created based on that. So in 1947, we have Graham, and he proposed that we have specific adsorbed ions. So ions, you lose the solvation shell. So the solvent will be, you won't have solvating the ions in here that will be in contact with the electrode. And you will also have solvated ions forming this rigid layer. With that, we have an inner Helmholtz plane, that is the specific adsorbed ions, and then we have the outer Helmholtz plane, that will be the non-specific adsorbed ions, right? That they are solvated. So we have this distance here. And one thing that's interesting, that they, Graham added the possibility of ions of the same charge. Like here we are polarizing the electrode negatively. We could have an ions specific adsorbed to the electrode, right? This was proposed because they saw in experimental data that changing the anion of the electrolyte would change also this region of the double layer of the capacity. So that could only be explained by having some anions adsorbed specifically to the electrode, right? So in this case here we have the 3 layers, right? Triple layer is considered. So we have the inner Helmholtz plane, the outer Helmholtz plane, and the diffuse layer, right? And then we have another increment that it didn't change the way we obtain profiles of potential and capacity, but added that solvent molecules would be also present in the double layer. So the amounts of solvents in contact with the electrode would depend on potential, and you also have specific adsorbed ions. And then you still have the inner Helmholtz plane and also the outer Helmholtz plane and the diffuse layer. But now solvent molecules would be participating of this double layer, what makes sense, right? So if you have a small potential and you have water, for instance, that have dipoles, it will participate of this double layer. And as you increase the potential to positive or negative polarization, then ions you start to make more, you have more importance in the double layer. So just to remind you that with this experiment here with sodium fluoride, we see that the diffuse layer capacitance dominates the region of the potential of 0 charge, and that the Helmholtz capacitance will dominate the region of larger potential, right? So I talked a lot about the potential of 0 charge, but just to show you that the potential of zero charge is related with when there is no change in the interface. So you are not applying anything. So the interactions here of electrode and electrolyte will be at equilibrium, right? So the position of this potential of 0 charge will depend on the electrode material and the composition of the electrolyte solution, because you can change this equilibrium, changing this composition. So for high background electrolyte concentration, most of the potential is dropped across the Helmholtz layer. So you have a lot of ions in the electrolyte, and then you have importance on the Helmholtz layer. For low electrolyte concentration, there is a significant potential drop across the diffuse layer. All right. Remember that anions can be specifically adsorbed at the electrode surface that is negatively polarized. So same charge, but being adsorbed over there. And there's one thing that's important, that the double layer charging, that is non-Faraday current, you will always be seeing experiments when you have change of potential. If you're doing a cyclic voltammetry, a potential step, or impedance, you are changing the potential, you are charging the double layer, and you have some current flowing through the external circuits. Remember that was the thing that I said in the first slide about the non-Faraday process. Okay, so now that we have this explained these models, let's think about measuring non-Faraday process. All right, so let's think about this cell here, and in the cell we have one mercury electrode and one saturated calomel electrode. We can describe electrochemical cells with physical circuits, right? So we have the capacitance of the mercury electrode here, and then we have the resistance of the solution here, and then we have the capacitance of the saturated calomel electrode here. So this is a way to describe it physically, right? So the total capacitance depends on the capacitance of both electrodes if they are similar values. If they have similar values, depends on both. But if you see this equation here, you can already tell that the total capacitance will be more will be closer to the smallest capacitance of both. All right, so if you have a small number here and a large number here, you have that this capacitance will be the smallest one. So we can say that we know that the saturated calomel electrode has a much larger capacitance than this electrode here, and then we assume that the capacitance of the cell, the total capacitance, will be as the capacitance of the mercury electrode. So this circuit here can be drawn as the capacitance of this electrode plus the resistance of the solution. All right. So everything that we measured during this non-Faraday process in this cell will be the results of this circuit. So if you apply a potential or a current, the measurement will be a result of this circuit here, this equivalent circuit. So any perturbation potential between these 2 points, the current that we measure will be the result of the currents passing through this circuit. Let's see how it goes. So deriving the equation of charge on a capacitor in function of potential, you get to this equation here. Okay, so current here vary depending on potential and time, and depends on the resistance of solution and capacitance, all right? So when we start the experiment, so we have time 0. So time 0 here. When you have 0 here, E over 0 will be 1. And then we have exactly E over resistance. So at time 0, we are applying a potential. So potential will be constant, but different from the equilibrium potential. So we have a pulse of potential, and it results in this pulse of current here. So current that we are measuring over time. All right, so we are measuring current over time. At time 0, you have that current will be equal to potential over resistance, and then we will have a drop of current related with this term here. Okay, so when we have 37% of drop of current, we will have this constant time, and this constant time here will be equal to the product of resistance and capacitance. All right, So this is the profile that we will see when we charge a double layer in a cell like that. Let's consider now a pulse of current. So you have the cell at open circuit potential, and then we apply a current, and now you are measuring a potential. So you're measuring potential over time. We have a jump of potential from the equilibrium potential to a potential that's equal to current times resistance, because this is time 0, right? So you won't have this part of the equation. And then we have a linear growth of potential over time that will respect the slope of current over the capacitance. So you can calculate the capacitance of the electrode considering the slope of this line here. All right, so these are those two types of pulse, one pulse of potential and then another pulse of current. Let's consider now a sweep of potential. So you have a potential E, and then potential sweep that E will be like E in that time plus a scan rate times time, right? So
sorry to interrupt.
Yeah,
We have a question here from
Mhm.
Rona. What is 0.37 E
okay.
divided by the RS? It's only to in the last slide, yeah.
Yeah. So here's that, respecting to this equation here, we have that the time will be equal to resistance to the capacitance, resistance times capacitance when the current dropped 37%. You see, so this is the first current here. When the current will be 37% of this value, we have this time constant. And this time constant is equal to the resistance times capacitance. This equation also tells us that when the current drops to 95% of this initial value, we have that the time will be equal to 3 times the time constant. All right. So this is just the value that we get from this equation during the variation of time. Okay. Okay. So back to sweeping potential. So the currents that we are measuring will depend on the sweep rate, right? On the rate that we are changing the potential. On the potential, on the resistance of the solution, because the current is going through here. And we have exponential term here related with time. So this blue line here is how the potential is being controlled. So we are controlling potential. So we are increasing potential over time. And the slope of this blue line here, that is what we are controlling, is the scan rate, right? So potential is increasing because we told the potential start to increase at this rate. And here you are measuring current. Sorry, here's wrong, it's current. You are measuring current over time. So we have exponential growth in smaller time, and then when time keep increasing, we have a constant value that will be related with the capacitance of this capacitor of the electrode, right? And the scan rate. So it's a product of the scan rate and the capacitance. And then we can change the direction of the sweep. So now we are decreasing the potential over time, but we are controlling it again. And then we have this kind of response, right? So first increase it, and then we invert it, and then we have the negative current, and then we are getting again back to the current that is related with the product of the current rate with capacitance. Remember that here is wrong, so it's current. We are measuring current and applying a potential. So you know that this profile is very known in electrochemistry. So we have a potential perturbation over time. So you have a measured current over time. And if you plot this measured current over potential, then we have the cyclic voltammogram, right? So we are applying a potential and measuring a current. And this is the kind of profile that we will obtain from a circuit that has only non-Faraday process or the charging of the double layer. All right. So, Thiago, I think I will make a break now. I'll do a break now. 10 minutes, I'd say.
Yeah, only 1 second, Vitor.
Yeah.
We have a question in the chat. It's about the tau. I think that is only to, I can answer that. It's only to define the rate in which the charge transfer of the electrode is established. To describe it, we describe the time constant as a constant value, Bruna. And until the break, Vitor, and there is a lost question here it was sent to me, not in the chat, from Rona to, in the beginning, when you were mentioning about the LUMO and OMO, the question is about how do we connect LUMO and OMO to electrochemical potential?
Yeah, so if you think that we are controlling, when you are doing electrochemistry, we are controlling the energy level of the electrons in the electrode, right? So changing the potential is changing the energy level. So the HOMO in the LUMO is actually the potential of that electrons in the solution. All right. So when we have when we change the I think I'll go back to that slide. Are you still seeing my? Okay, here. So here we have on the left the electrode and on the right the solution, right? Think this as the actual electrode. So when you have any species in solution, let's say that we have iron here, and we have the HOMO and the LUMO of the iron, and this is the energy of them, right? And when you are not doing any electrochemistry, the electrode will have an energy level of electrons between those two. So there's no reason for electrons in the electrode to jump to the LUMO, or from electrodes from the HOMO to jump to the electrode, right? So changing potential is changing the energy level of electrons. All right. So if you change the potential, so this value here, you have the same energy of the same level of energy in both electrons. Electrons in the electrodes, and the energy that we have in the LUMOs, right? So we don't have electrons here, but we have this is the lowest unoccupied molecular orbital, right? So when we have both energies here are the same, let's say here, so you have this case here, you have electrons here and we don't have electrons here, and this is the potential that I needed to increase the energy level of the electrons in the electrode for this reaction to occur. So that's how the potential is connected, you see? So it's the potential that I needed to apply to raise the energy level of the electrons in the electrode to be at the same level of the LUMO here. So that's how potential is related. I hope that clarifies.
I think it's yes. And
Okay.
I only check if they have, no, we don't have any more questions. Okay, we will have a 10 minutes break.
Okay.
Or 15 minutes, what do you think?
No, 10 minutes, I think.
10 minutes?
But,
Okay,
yeah.
perfect.
Okay.
We'll go to a 10 minutes break. Oh, only Vitor, could you stop to share your screen?
Okay.
Oh, we have a question here. Someone raise their hand. Andrea, I will open your mic.
Thank you. Thank you. I just wanted to ask a question about HOMO and LUMO, and I thought it was too long to be written. And can you hear me first?
Yeah, perfect.
Okay. And according to this explanation, that we have the redox potential when the potential of the electrode is at the same. Oops, open the cam. Okay. Is at the same potential of the LUMO or HOMO. This means that there would be two redox potential for one redox couple. Is that correct? Or I misunderstood maybe?
Mm-hmm. Can you see my screen yet?
Only you, Vitor. If you
Can I see
need
my
to
screen?
share the screen again.
Mm.
Yeah, now we are seeing your screen.
So actually, what we are seeing here is that for one reaction to occur, let's say, we have this reaction here, A plus electron going to this ion, right? So for this to happen, you have to change the energy level of the electrons in potential.
Mm-hmm.
Using potential, right? So you only have a reaction if the potential of these electrons are in the same value as the energy levels of those orbitals. All right?
Mm-hmm.
Is that the question?
No, my question was that in this way, we would have two redox potential for a redox couple. One potential for the reduction, if the potential of my electrode is at the same level of LUMO, and one potential for the oxidation, if I am at the same potential of HOMO. And I was asking if I get it wrong, maybe, or if it is the case.
No, you have only one redox potential for, like you see in the table, right? No,
Yes.
I understand your question now. Can I answer after the break? I will check in the book actually.
Okay,
Yeah.
no problem.
Yeah.
We'll do the break, and after the break, we can answer your question. Perfect.
Okay. Thank
Okay.
you.
Always, you will stop to share your screen, Vitor, now. Thank you. We will do the break, and it will return in 10 minutes. Hello, everyone. We are back here. And Victor, you prefer to start to asking the question or
Yeah.
you share to? Perfect.
I'm sure it's the screen already here.
Perfect. You are sharing.
Yeah. So I will answer this question tomorrow. I have a guess on that, but I would like to be sure. All right.
Perfect. No problem.
On Susanna's lecture tomorrow, she'll talk about it, and then I will send to her this question and the answer to her, so she can talk a little bit on that. Is that all right?
Perfect.
Yep. Okay. All right, so we talked about the non-Faraday process and ways to measure it, all right? And the next 40 minutes, we talk on Faraday process and ways to measure it and what impacted this process, all right? So a Faraday process has electron transfer occurring across the interface. So the driving force for this to occur is this difference of potential, right? So remember that we are applying a potential on the metal, and this is the distance from the electrode surface, and how the potential drops in the electrolytes. So the driving force for the electron to be transferred from the metal to the species in solution, or from the species to the electrodes, will depend on this drop, right? So remember that the driving force is the difference of potential of the metal and the solution. With that, I would like to show you that we have two types of cell. A galvanic cell, it's when you have two reactions occurring, one in the negative electrode and one in the positive electrode, with electrons flowing through the external circuit, but this is spontaneous, right? So you just connected the circuit, and then we have the flow of electrons because of these two reactions. In a galvanic cell, the negative electrode is called anode, and the positive electrode is called cathode, right? And then we have the electrolytic cell. The electrolytic cell is when we have the electrodes in solution, but if you connected the external circuit, we won't have the reactions occurring. We need to supply the driving force. So in this case, you have a battery here, and then the reactions will occur because we're forcing it to occur. So in this case, you have the anode as positive electrode and cathode as negative electrode. You can think as in a battery, like a lithium-ion battery working as galvanic and electrolytic cell. When we are using a phone, you are not plugged to the wall, so the energy that your phone is using is coming from the battery. So you're just connecting the external circuit from the battery and using the electrons that's being transferred from one electrode to the other electrode. And then when we need to recharge the battery, we are applying the potential over there. So we are giving the electrons for those reactions to occur. And then your battery is working as an electrolytic cell. Okay, so this just as an example for you. If you see here, in just two types of cells, you have the same reactions as examples, right? So you have reduction of copper occurring here in the galvanic cell, and also reduction of copper here in the electrolytic cell. And of course, electrons is going to these electrodes. In electrochemistry, we are actually normally concerned about one of these reactions, right? So it doesn't matter actually how it's working, but it matters what you are measuring. So we'll see more this on this next slides. So what we can measure is basically as before. So we have current in amperes, amps. That is the rate of charge, remember? So coulombs per second is current. We also have the overpotential, that is the difference of potential against disequilibrium potential. And we can also use the Faraday law of electrolytes to relate number of species being produced or consumed depending on the amount of charge that's crossing the external circuit, right? And we have rate, so we have mole per second of products being produced or consumed, and that is related with current. All right, so remember that current is the rate of charge crossing the external circuit per time, but it's also related, because of that, is related with the electrochemical reaction that's occurring in the electrode. So let's consider one simple reaction here. So we have one species being reduced, and it is at equilibrium. So we have a dynamic equilibrium. So both reactions are occurring at the same rate. So the speed of the reduction is equal to the speed of the oxidation. So the current that we are measuring is equals to 0. So the cell is, you have the cell connected to the potential stat, and you have a reaction that's at equilibrium in the electrode surface, right? What we are measuring is the open circuit potential, that will be the equilibrium potential, and then you are measuring 0 current. But actually what we have is that the current of the anodic reaction will be equal to the current of the cathodic reaction, all right? And then the total current is the sum of these two currents. So one minus the other is equals to 0. but also, this is wrong, this should be here. When both currents are the same, we have the exchange current, all right? And this cannot be measured directly. It can imply something to obtain the exchange current, but it can be measured directly because we are measuring the total current. The total current is the sum of these two currents that's related with these two reactions, all right? So at these conditions, when we have the equilibrium, we have that the Nernst equations and the potential will be related with the concentration of the species in solution. So if you change concentrations, you can change the potential, all right? So if the electron transfer is fast, you have equilibrium. The concentration of the species are at equilibrium too, and then the Nernst equation applies. So what we have is that if we apply a potential, a positive over potential here, we will make that the reaction of O of R turning into O will be faster, and then an anodic reaction will flow. An anodic current will flow. If we apply a negative over potential here, and then the reaction of O turning into R will be faster than the other one, and a cathodic current will flow, okay? We have two types of electrodes here to understand. Is the electrodes that are considered polarizable and the ones that are considered non-polarizable. So the polarizable electrode, we can apply a range of potential where we have no current flowing, okay? So we have all this region here where there's no current flowing. On the other hand, the non-polarizable electrode, you have a really small change of potential for a large flow of current, okay? So this is a reversible electrode, and you see why we measure those kind of results. We can think on this electrode as equivalent circuit of a resistance and a capacitor. So we have a resistance here and a capacitor. And to change the potential, the current needs to go through the capacitor, right? So imagine this is the electrode, and then to change the potential of the electrode, the current needs to come through here because you are charging the capacitor, and charging capacitor change potential. So to change potential, to polarize the electrode, the current needs to go through the capacitor. Let's think of these cases. So if you have a high resistance here, the flow of electron will prefer to go through the capacitor. And then we have polarizable electrode, right? Because you are changing the potential here. So this change of potential is related with charging the capacitor. And if you have a low resistance, then the electrons will flow through this resistance instead of the capacitor. And then we don't have a change in potential. So the current is only flow through these resistances. So reactions that have low resistance or low electron transfer resistance will have a profile similar to that. So potentials can be changed in the polarizable electrode and does not depend on concentration. And in this case here, the potential is determined by the electrochemical reaction that's occurring and the concentrations. And in this case, Nernst equations apply. So let's remember a very important difference between, let's say, normal chemical reactions that we do in a beaker or in a Ronald flask, and an electrochemical reaction that we are doing using electrochemistry. When you do a reaction in a random flask, this reaction will be homogeneous, right? It's happening all over the solution or the flask. In an electrochemical reaction, you have the reaction only at this electrode surface. So it's a heterogeneous reaction. So it's not occurring everywhere of the solution. So let's say again that we have this simple reaction here. And when we start to have this localized reaction, this will have some impact on the surrounding of this electrode, okay? So let's say that we are consuming a species here. So we have a reduction of O to R. And then what needs to happen for this oxidation to occur? The species that is in the bulk of the solution needs to get to the electrode surface, all right? So we have mass transfer between the solution, the bulk of the solution, and the electrode surface. Other steps can happen, like adsorption and absorption of species. Then we have the electron transfer, and we can also have or not adsorption, and then this product needs to go to the bulk of the solution, and then we have mass transfer again, all right? So you see here that we have some steps occurring for the actual electrochemical reaction to take place. In the simplest case, let's consider the simplest case, you have only mass transfer. So the species is coming from the bulk solution to the electrode surface, and then we have the electron transfer. So we have a resistance of this mass transfer and a resistance of this charge transfer. So if you think of the simplest case, the whole process will depend on the slowest step. All right. So if you have a resistance of mass transfer that's much bigger than the resistance of charge transfer, the reaction mass transport, the reaction is mass transport controlled. The other case is if you have a resistance of charge transfer much bigger than the resistance of mass transfer, you have that the reaction is kinetically controlled, all right? So the kinetics of this reaction here, you dominate the whole process. So we can think on how the current will vary depending on these two processes, all right? So in this red curve here, we have only the activation current. So only considering that it only depends on the kinetic of the reaction. So you don't have problem with mass transport here. And the green, we have this area of mixed control, where we have both kinetic taking place and also mass transport taking place. And then when you reach a potential that we don't have any trouble with kinetics anymore, then you have the limit current, and this is the mass transport control. So activation region, mixed control, and mass transport control. And the total current that you are actually measuring, will be the sum of these two currents. And again, the smallest one will dominate the total current, right? When we have a high enough potential, we can say that we have the limiting current, and this limiting current will depend on the diffusion of species, the concentration of the species in solution, and also the diffusion layer. All right, so this is one equation, important equation, that we see in details in the further slides. But before, let's talk. So with that, in this slide I showed you before that the Faraday process depends actually, in the simplest case, of two processes, right? So mass transport and the kinetics of the actual electrochemical reaction. And then let's talk about the mass transport. We can have three types of mass transport, and mass transport, you can think like the flux of species that is occurring because of some force, all right? So the flux of this species is in mole per square centimeter per second. And the three types of mass transport that we have is convection, that follows the Poiseuille law. And convection can happen in an electrochemical cell because of difference of pressure, changing density of the electrolytes, or changing temperature, right? So we have this relationship of flux with this pressure here over the distance. Migration is the second type of ions movement in the electrolyte, and migration occurs due to Ohm's law. That is the difference of electrostatic potential that can be measured in current, right? So we have a difference of potential in this distance, and then we have movement of ions because of that. And then we have diffusion, and the diffusion goes with Fick's first law, and it's because of the difference of chemical potentials. That is actually difference of concentration. Remember that I said that the species need to go from the bulk solution to the electrode surface, and this is occurring during because of diffusion, right? So we have higher concentration bulk, lower concentration on the electrode surface, and then the species will go with diffusion from one point to the another point. All right, so this is a difference of concentration in distance, and we have those constants here. So all these three types of mass transport can be used to get species to the electrode surface. All right, and the use of these different types of mass transport will depend on your application or on your study. All right, so you can summarize this as the electrode here, and then we have the bulk solution, and in bulk solution we have migration and convection happening, and in the inertial diffusion layer we have only diffusion occurring. All right, and the thickness of this layer will depend on other things like concentration and especially convection. So let's think of a few examples and the movement of these ions, right? So you have a negative charge electrode, and we have copper 2+ here. If we are applying this potential, right? So the copper 2+ will move because of diffusion. So this reaction is occurring. So I have less copper 2+ at the electrode surface than the bulk. So we have diffusion occurring here, and you also have migration, right? Because you have a negative charge here and a positive charge here. So have two the total current of that we are measuring will be the sum of the currents doing to the diffusion plus the currents doing to the migration. So if you change the species here, now we have a negative charge species, and then we have a current due to the diffusion because this reaction is occurring, right? So we have this current due to the diffusion, but then the current due to migration is in the another direction because both are negative charge. Then the total current will be the diffusion current minus the migration current. In the last case, you have a species that has no charge, and then this reaction is occurring, and you have only diffusional current here. So total current will be equal to the diffusion. Normally, in the lab, all right, we avoid convection by controlling temperature and making no perturbation to the cell, and we avoid migration by adding support electrolytes. All right, so high concentration of a salt that will not react or go through electrochemical reactions. But there are other techniques that use convection, all right, to improve this ions movement. So rotating disk electrode and agitation are forced convection, right? So again, that depends on the application or what you are studying. So I said to you that you have the inertial diffusion layer here. This is typically the range of size of the inertial diffusion layer, and that depends on potential and also depends on the mass transport regime. If you have forced convection, for example. You have a relationship of flux of electrons and reactants. So you have electrons in this case here, and the diffusion of reactants here. And if we have a large enough overpotential, we can say that the species that's being consumed is equal to 0 at this electrode surface, then the reaction only depends on the diffusion of this species from the bulk to the electrode surface. And then we can write that first equation I showed you. So the limiting current is when we have the concentrations here equals to 0, and then we have this relationship of limiting current that depends only the diffusion, and we have this constant here that is the mass transport constant, all right? We also have that the inertial diffusion layer depends on time, so we are applying the potential, and this is the relationship of the concentrations, right? So as time goes on, this profile changes, all right? So each line here is a different time after the potential was applied. And then the other thing that impacts the current in Faraday process is the electrode kinetics, okay? So remember that we have this reaction occurring at equilibrium at the same time. So we have the reduction from left to right and reduction and oxidation from right to left. And you have the rate of these reactions. The rate of the reaction of the reduction reaction will be the rate constant times the concentration of this species, and the other way around as the same. So at equilibrium, we have that the rates are the same. So we have this this relationship here. And then we also, when we have that, we say that we have a potential of 0, right? So the potential that we are measuring is the equilibrium potential. So here I'm showing the current. So just to remind you that current, the symbol of current is I, and the symbol of current density is J. So current density is just the current divided by the area of the electrode. And when we have equilibrium, have the current of the left to right reaction is equal to the current from right to left reaction. And this is the exchange current density, right? So remember, both reactions happen at the same rate. And the rate constant depends on E, and I will show you how. Okay. So back here to the firm level, so we are changing the potential. So making a reduction reaction to occur. When we change this potential, as the rate constant depends on E, we are making this reaction on this way happen faster, to happen faster than the reaction this way. So potential is lower than the equilibrium potential, and then this the constant rate of this reaction will be higher than this one because they depend on potential, right? And the same things is true on the other side. So if I increase potential positively, then the potential will be greater than the equilibrium potential, and then this rate will be greater than the other one, and oxidation occurs. So to see here how the rate constant depends on potential, we have those equations here. I'm sure tomorrow you'll see this more closely. So the constant rate depends on the standard constant rate, and this is standard constant rate, rate constant, sorry, is when you have concentrations of both species equal and the potential is at equilibrium. So the system is at equilibrium. So this is the value of the standard rate constant. And the rate constant of the reduction reaction will depend on this term here. That depends also on potential, right? So when we are applying a negative potential, we are increasing this value here positively, right? So that's how those rate constants varies with potential. So when you're applying a negative over potential, the rate constant for the reduction will be much bigger than the rate constant for the oxidation rate, right? And the same thing occurs when we apply a positive over potential here, and then this get bigger and this one gets smaller, and then we have a larger rate constant for the oxidation reaction than for the reduction reaction. Then we have the Butler-Volmer equation, just to show you how it's not the intention here to define the Butler-Volmer equation, but I just want to show you how the exchange rate, the exchange current is important. So I have three cases here. I'm showing you the equation here. So current depends on the exchange current, and these two terms here that are the oxidation and the reduction terms depending on the potential, right? So as you change potential, one will get more important than the other. And that's how one reaction you gain more value than the other, right? And here's how the current that we measure here is changing with potential when we change the exchange current. So for a very small exchange current, we have a curve like that. So we need a larger over potential to the current to occur. So remember, this means that we have a higher resistance. Remember that from the polarizable electrode. So a higher resistance to the electron transfer to occur means that this reaction has a low exchange current. That's why you get a profile like that. And then if I have intermediate value for the exchange current, we have a profile like that. And if I have a very large one, it means that the resistance of this charge transfer is so low that we don't have any change in potential during this flow of electrons, right? So this will be like the ideal case of the non-polarizable electrode, as I showed you before. So this is a very large exchange current rate. So I also want to show you how the Tafel equation can resemble the other graphs that I show you. It relates here again from the Butler-Volmer, and then we can consider just one reaction happening, and you have the current depending on just these two terms. And then we can plot a log-log graph here. So this is showing currents in function of potential, and the bottom one is showing log of current in function of potential, right? So if you remember from some previous slides, I show you have the activation region, the mixed control, and the mass transfer control.
Sorry, Vitor.
Yeah.
We have a question here in the chat about the alpha, to try to talk a little, what is the alpha equal to 0.5?
Okay, so tomorrow you have a class of mass transport and kinetics, all right? So my intention here is just to show how the potential can change the current in Faraday's process, but the alpha is related with the symmetry of this reaction, okay? So you can change, you can have different values of alpha, but here we are considering only alpha as 0.5, and it can vary from 0 to 1, right? So normally we will consider 0.5, and this is related with this symmetry factor, and this is related with the reversibility of the both reactions. But you'll see this more closely tomorrow, right? So this graph here is similar to the one that I showed the previous slides, just to show you that if you plot the log of current in function of the over potential, we can see some interest parameters from this reaction, okay? So when you have this log representation, you see here that I'm showing that alpha is equal to 1 when you sum both, just to show you that is considering 0.5 actually. So we have that at smaller over potential, when we have activation region here, on the log representation, we have a linear dependence with the over potential, and the slope of this region depends on the symmetry factor of this reaction, okay? And now for both sides, so then we can have an idea on the symmetry factor of this reaction. And when the over potential is 0 for this slope, so we can have a value for your exchange current. So the form of this TEFL plot will depend on the value of the exchange current, and the slope will depend on the symmetry factor, all right? And then we have here the mass transfer control, and the value of this log current here will be the limiting current, right? That depends on mass transport. Okay, so as I said, the idea was to show how mass transport and kinetics impact on Faraday reactions. And here I have both equations showing both extrapolate cases. So here I have limiting current that depends only on the diffusion and the concentration of the species. And here we have the current when we have a kinetic dependent reaction that depends on the kinetic of the reaction, on the over potential and the symmetry factor. See here that we don't have dependence of potential, right? So this table just summarize this last slides. In the last slide, I will talk about reversible and irreversible reaction. And when we say that an electrochemical reaction is reversible, we are thinking about the thermodynamic sense, right? So the reaction at the electrode surface is at equilibrium, and then the next equation applies, okay? So that this the concentrations on the electrode surface can depend on mass transport. and that depends on the experimental design of your cell. Okay, so if you have a rate constant that's much higher than the mass transport constant, we have that this electrochemical reaction will be reversible. So species concentrations depend on the Nernst equation. And if you have this case, you only can obtain thermodynamic parameters from your experiment. In the case that we have a rate constant that's much smaller than the mass transport constant, then we can say that the electrochemical reaction will be irreversible. And the species concentrations depends on the Butterworth equation, all right? And you only get the kinetic parameters from experiments. So designing your experiment depends on what we want to measure, all right? What if you want to obtain kinetic parameters of a fast reaction? So if a reaction is so fast that depends only the mass transport, we have this case here. In this case here, we only get thermodynamic parameters, right? But you want kinetic dynamics. What can you do? We can design an experiment where mass transport is rapid. So we can use convection, for example. Then we will measure, we can change the mass transport coefficient here and measure different currents depends on this, on this constant. And then you can extrapolate considering this mass transport constant to infinite, and then this extrapolated current will be pure kinetic, all right? But how can you do that? We'll talk about tomorrow. So I just want to say that those slides were based in this, especially on these 3 books, all right? And each slide has the reference for the book. I think Thiago will send maybe the slides to everyone, I don't know. But if you see the lecture later, the slide has the reference that slide was based on each book, all right? So that's it. I think on time, right?
Yeah, perfect timing. Thank you, Vitor. I will send the slides, and the slides, the lecture, all the lecture will be available on YouTube too. And thank you again, Vitor, to help us.
It's a pleasure.
And Rona is giving thank you to you. There is a question from Marcia Fatima. From one last question until we finish. The potential equilibrium is in overpotential in the Tafel plot. Is it from Nernst equation?
Yes.
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 There's another one from diffusion and convection, but I already answered in the chat. And there's everybody giving thank you to you.
Thank you.
And thank you very much, Vitor, to help us.
So I have one question yet to answer that I will talk to Susanna.
Oh, yeah.
So she will answer tomorrow, right?
Yes. I will only give one other another announcement. When we finish this week, I will send the certificate of participation for everyone. But it's important that everyone will be attended to all the lectures. And this is my last announcement today. And with that, thank you again, Vitor. Thank you everybody to attend today. And we see everybody tomorrow in the same time. And thank you very much for all.
Thank you very much for your attention. Thank you.